Yeah, welcome. And I'm give a talk about a lock that's long been considered unpickable in very vague terms. Uh, we run across to these locks in Finland quite a lot. These are old locks. And of course, old safes have problems and people want them open and keys are lost. So it's ongoing research, and this is the first time presentation about this whole thing. So if you see or know something missing, yes, I will eat it. So if you see something missing or know something about these locks, I'm happy to hear after the talk. So let's click on. So this is basically what we are dealing with. Just quick topics about things. And it's free to photograph everything. You can get a copy of these slides later. It's a large file, so have some memory stick or something. Uh, my name is Jaakko Fagerlund, as noticed, and I'm coming all across the globe, second year here, and interested in safe openings uh, more than a hobby, because I own a company that opens safes, whatever locks actually. Uh, and day job is just doing tool and die work like molds, dies for cutting things, basically machining. So it goes very well in making tools and playing with locks. Uh, this is the Kromer protector in parts. It's not a lot of parts. Uh, one could describe this lock as a wafer lock, or lock with a lot of sliders. I classify it as a wafer lock just because of the shape of the little uh, wafers. There's no spacers, nothing, so they just slide in and out with the key. So the key will force them into place. And sorry about the dark pictures. This is my phone camera that I used. I'm not a professional photographer also. Uh, Here's a little quick screenshot from Coxa's wiki page, which has a lot of information regarding this lock, unfortunately in German, which I vaguely understand. But you can easily see it goes, the whole history of the lock goes to 1874 with one of the patents. There might be even something older. So the lock is well over 100 years old. And considering the amount of patents, this is just the first page of the list of topics on that page. Um, there's been major revisions once in a while, of course, people adding more and more stuff to it. I've never gone through all the patents, but some of them describe just additional security features regarding making the lock harder to decode or to read the key. That was the basics of this lock, being a key that is very hard to duplicate, or having a lock that is impossible to just look inside and see what the key would look like, because there's all sorts of extra cutouts and everything in the little lock parts. Uh, this is basically the heart of the lock that you will try to turn. So the core is here, just a piece of round where all those little wafers sit in. There's a little drill protection plate on the bottom. For some reason, it's locked in place in terms of it doesn't rotate freely. There's also, you can see the post sticking out from the middle of the core, which is typical in safe locks, that reduces the space available for any tools. Um, and here is the core sitting in the body of the lock. So it's just a larger round piece. And it has a very tight tolerance, like it fits just perfectly. And some of these locks I come across are unfortunately greased. I don't know why, because it works better when it's dry. Here you can see I've turned the core clockwise just to show that what actually moves. So in this little slot here, if you go back a little, oops. So here's the slot for the wafers to sit in on both sides. So that's the shear line. And here you can see it's been turned. This is wafer number 1 from the lock, so the first one you assemble. So from the keyway, it's the deepest one. And this cutout doesn't resemble a key at all. You have no idea where the key will actually touch in this, other than it's somewhere here, roughly. Some keys have points that touch this, some will touch that, someone will touch there. And there's only one spring that is pushing it out. There are very weak springs, literally weaker than in a pin tumbler sometimes. But they're not required for the operation that much because the key will force this into place. This is the number 1 wafer inside the core. So in here you can see it's not at shear line, and here it's past the shear line. So it locks on both sides basically. It's double acting wafer. So if you push it in too much, it will block here. If you don't push it enough, it will lock here. And this is the same wafer turned just enough to keep it in place in the open position. And if you find a lock that has not been modified by somebody, these wafers are exact length in this core. And I will get back to this later regarding how they actually make this lock, or how I think they make this lock, because it seems that it's not exactly cheaply made. I've heard stories of this lock costing somewhere upwards of €5,000 a piece with 2 keys. Here I tried taking a picture of the key with the wafer number 1. It's been turned open, so in this configuration it touches that part of the wafer there and also there. So it will basically, the key will stop the movement of the wafer in 2 directions when turned, if it's the correct key. Here's a wrong key. It turns way too much. Like normal position for a key to enter would be vertical. For it to open would be roughly 45 degrees, and this just turns way too much. The cut is too small in the key. So I went through 30 of these locks. We have, with my friend, a collection of these to research. All of them mostly the same, and we measured the actual rotation of the key, how much can you turn it for the lock to start opening, and we discovered that it's roughly 45 degrees. It's not exact, but that seems to be the middle ground there. And if you try to use a wrong key, it either doesn't turn or turns too much. Mostly it doesn't turn enough. So it's a wafer lock, so of course we make it secure by adding more wafers to it. So here's the whole lock filled up to the top, all 11 wafers. And a nice little diagram of the key being turned to open, so all the wafers are aligned on both sides. It's starting to rotate, and that angle is roughly 45, depending on the lock. That's a wrong key for the same lock. As you can see, that's the original key, and this is the wrong key. So it's pretty much not going to open. And here's a little close-up of the wafers inside the lock on the side. Normally there's a little blockage or a little piece of metal covering the wafer stack, probably just so there's no dirt getting into the lock from the safe door. And that 11 wafers basically all have some special functions in them. Mostly they just test different parts of the key, like for example, is the blank correct shape, size, is all the angles correct, and so on. There's a lot of little tiny details in the key. And I can actually put one of the locks in rotation so people can see. So that has one working key on it, and feel free to turn it, it doesn't break. I removed the side panels from it so you can see the actual wafers. That lock has been modified a little. It's not original, but this is the thing that locksmiths do. They modify things because you can't get spare parts for that easily. So we've been looking at those wafer shapes and trying to figure out what they do or what they do not. And for most part, all the wafers just are there to add complexity to the whole lock in terms of lock picking or lock decoding. And one thing we haven't figured out or heard from anywhere is why one of the wafers is steel. And then there's, depending on how old the lock is, the ones we run into like these have what we call split wafers. So there's actually just two parts which are almost identical. So the key has to position both of them correctly, and when they're correctly positioned, they're sitting in the lock like this, nested together. So you can push this one way or the other as a whole packet, but that's wrong for the lock to open. And these can be found on position 3 and 5 in the lock. These are all stamped, so there's a number 3. This is the third wafer. But usually the other wafer has a stamping that says 3/5, so it can be used in both positions. Then there's the number 4, which regards the closing of the lock. So when you open, the key is touching these ports here marked with the red. So that's actually a place where the key blank side touches. The actual cut doesn't do anything. On this side, cut actually does something. It has to be correct. But when you're closing and the key is vertical, this is basically, you could say it's the tensioning wafer that will turn the whole thing backwards for the lock to relock again. And this also shows quite nicely that there's extra cuts just because it's making it much more difficult to decode. And every wafer basically has different shapes of these. Also visible on this wafer nicely is these little grooves. That is just a way to get more space for the springs in the next wafers. So it's just a little space addition. Here's the wafer 4 with the key, and the core has been turned a little. These are actually very hard to photograph in the open position because there's the springs trying to push it open or closed. And in here I marked with an arrow the place where it tests the side of the blank to see if it's the correct size. Then number 6 wafer, again, totally different shape. So no idea where the key will touch. But this is actually almost always has been the same wafer in every lock with a key that has a little groove on the side. I think the one that is rotating here has a key with a groove. So this will test the existence of that groove and mostly the end chamfer of the key. Because if the key doesn't have a chamfer, this little part here, this little knob, will rest against the post that is in the middle of the core, and it will prevent the key from entering unless there is the little chamfer to push this aside a little. And here's the picture of the key. That's the groove for the little part. This groove is actually not required for the lock to operate. You only need that cutout, that little groove, to lift it up on that little angled cut. That angled cut actually positions the wafer in a place that it would be the same as you would have this blank stem, 7 millimeters in diameter, just sitting there, and the number 6 wafer is correct at that point. So it's kind of just a checking wafer, except on the other side of the key, on the opposite side of the key, there's a cut that needs to be correct. So it's not just only for checking something, there's always some code part also. So here's the key inserted halfway, going into the lock. You can see the wafer's little knob is just sitting on the edge of the groove, and it's not going into the groove at all. So the existence of that groove is not critical. This is roughly patched image, but it should show here the key touching basically that knob with the angled cut. So the key is turned. This is the normal direction of the key when you insert it. Then we jump to wafer 9, and this has a special feature in the key which is impossible to duplicate on a normal duplicating machine because the key has an angled cut. It's strictly not necessary to be there. You could make a normal cut on the key to mimic the right shape, but this is actually done on a wafer, so they drill a large hole and cut it off from here to get this little springy piece. And on the underside of the wafer, there's a little milling done to get it thin. So this actually will bend in the lock into the key. Just a little, but this is also one of the wafers that is always the same. That angled cut is always there. So this is the cut, slightly slanted. It's always the same depth, always in the same place. And there's the wafers cut out for it. So if you insert it and turn, it will go into the key. That little piece has bent down just a little. It's probably 0.2, 0.3 millimeters, but just enough to actually bend. Then is the mystery wafer that we still don't understand why this is still, but it's always the number 10. And this has the specialty of having the key code or half of the key code stamped on it. So it's very easy to check the the wafer pack for what key actually works in it. If you just remove the top wafer, the number 11, to check this number, if it corresponds with your key, you know that these parts will work with that key. For some reason, they always omit the 3 other numbers. The key usually has 6 numbers on it. Maybe space reasons, maybe security, I don't know. But these are not visible from anywhere when this is assembled. You cannot take a scope into the keyway and try to look because these wafer stacks are basically with 0 tolerance in terms of space. Then the number 11 wafer has a little specialty in terms of it has no springs and it's split. So this is hard for lockpicking reasons, because there's practically no way to typically move it the other way, except this also provides the possibility, because these will move each other. So if you push the other one too long or too much, it will push the other one back. So it's hard in terms of if you set it correctly and then you move the other, you can easily unset it and the lock basically resets. You hear that nice little click and you're back at the beginning with the picking. And one of the strange features in some locks is the ability to lock them with any key. Just push something in and turn it to lock. And this is one great way of people locking their keys inside the safe, because they have a safe that might have two of these locks with different keys. And they think they look the same, just put the other one into the safe and lock it. Well, it locks perfectly, but now you only have one key to open one of the locks. And usually at that point when you ask, there's no spare key anywhere. So what they do is they chamfer this little end or edge here on the body. So some of the wafers do not have to actually be correct when you're turning to lock. They can protrude a little from the body or the core, and it still can push it in. So here's a little diagram, the first wafer only. So it's now locked, and there's the chamfer that's there and there. So on this side, the wafer is protruding from the core into the body. But if you start turning it, that little chamfer forces the wafer to be correct, and it allows the lock to turn to the locked position, so counterclockwise. And just for the record here, there are both left and right-handed locks, so that's even more difficult regarding tooling. But this is the standard stuff we have been finding from all these locks that we have. So wafer 1 always has one side of the key the same. The other side of that has some sort of code cut on it. Wafer 4 usually has the just checking function for the blank or return function. The 6 is always the same. The number 9's angle cut is the same, the one that is not like any other. And the wafer 11 is usually the same, but not always. So it's really difficult to figure out, because these locks do not have any dates on them, like when they were manufactured. They just look the same, and it just reads DP patent on the front of it, so it's impossible to say if it's from even the same decade. So that's the reason for the little disclaimer here. But all the other 6 wafers usually are just something relating to the actual key code that will change. And the key code being 6 numbers long makes interesting ideas regarding this thing, but it doesn't exactly collaborate with this, because of course all these 1, 4, 6, 9, and 11 have always the opposing side on the key with some sort of code cut on them. The keys themselves are asymmetrical, so the lock that was going in there, you can see from the keyway that the other side is a little longer than the other end of the key. Typical cut is like any safe lock key has, it's just a cut to a certain depth. But then some of the wafers have angled cuts. They actually are not angles in terms of like an Abloy or Abus locks. It's just a angle cut to certain depth. Then there's on the key, there can be on some keys I've seen decoys that are basically cuts on the side of the key that doesn't touch anything when you turn it to open. It's just there to make it look fancy and difficult to figure out. So if you don't know anything about the lock, it's impossible to make a key easily. And we have been testing those wafers, and with a key and a little bit of shim stock, you can test of how much off the key can be for the lock to still open. And this plus minus 0.1 millimeters is roughly the correct answer. You usually can, some cases, use 0.3 millimeter shim and get it to still open, but usually not. The actual keys can be very long. The ones rotating here are just detachable a little bit. You can have 1 meter long key if you want or need, and that's quite typical to see in a vault door. They can have a little foldable stem, or they can be just solid like any other long key. And like I mentioned earlier, there's the thing that it's right or left-handed. So on a key, the groove is on the other side, as well as the angled cuts, or basically mirror images. And what we discovered is that wafer positions 3, 6, and 9, they always have an angled cut on one side. So here's the difference between two keys. That is a right-handed key, so turn clockwise to open. And this is a left-handed key, turn counterclockwise to open. So you can see the leading chamfer on this end is on the opposite side here. And also the little groove going here, in here it goes that way. Also, here's a good example of the groove that I mentioned. It doesn't do anything on the side of the key. This is from all the way from the end of the key. This is just a little groove here. So it's basically just a lead-in for this actual cut that is on the side. There's a comparison on some of the keys on when there's the one little angled cut on position 9. On the opposite side there's a little dimple. I've never figured out any explanation for that dimple in terms of what it actually does. It does cup the number 9 wafer on the other side, but I'm not sure if it's actually needed or not. But it's usual to see this on some keys, but not all. And this is also a good example of position 3, 6, and 9 having that angle cut. So it shows up as a dark spot here. All the other key cuts are just like any key cut, they're just depths. And so this is one example. The lock that is going there should have a key stem like this. This is actually from Kassakaappi Oy, Finnish maker, nowadays known as Kaso. They use these a lot in their old safes. Then there's the foldable stems. We somewhere have even one longer one, but it's just to make it easier to carry or put in your pocket. Of course, the longer one starts to be the size of, it's not going to fit in anyone's pocket, even when folded. So I don't understand the reason for having this long key that folds just halfway. And then there's very long keys. This is the longest that we have in our collection, though we have seen a key that was almost 1 meter long. That was not factory made, but somebody else had made it. And from the collection, I found a holy grail. Apparently I don't have the keys here, they're in the other room, but you can see them if you like. These are key numbers 253, 418. The other one is otherwise the same, but it's 419. So it's the next key from this one. We're like, well, holy hell, now I know what the key code actually means. What does it do in the key? Well, it does this. It's not easy to say that the keys are numbered just one off from each other, because there's actually 3 different cuts here. Like 3 different points have changed. But last year in LockCon, I think somebody told me that they actually permutate the keys, so within certain code range, the code number changes, they have the same cuts on the key, they just switch them around. So you can see here the long cut here is there, the little shorter one is there, and that angled cut is there. So they just switch 3 of them around. And this is the fun part, they actually just change the key. Usually the wafer might be even the same in the locks. This was one of the strange keys that we found. It has a code 225056, but the end cut, like here's the lead chamfer on the key. This is the side of the key that never changes, it's always the same. But on the other side, this was the first key ever we saw an angle cut. Every other key just has a depth. So a little bit strange, but okay. It might be an old one or a different version. We don't have the lock that goes with this key. We might think that it's a different model. And because this key actually shows quite nicely the blank shape, there's a rounded end to it on both sides. I started looking at the keys and doing measurements. I listed the key number and then measured on both sides the front of the key, the wafer 1 position on the key, like what kind of rounding it has, like how many millimeters of radius it has. And I discovered there can be 3, 3.5, 4, 4.5, 2.5. So it's all around the place. It's like there's no actual logic to it. It seems to be it's random or not. Again, sample size is only 30 keys, so hard to be completely sure. And one of the oldest ones was this one. It doesn't have 6 numbers at all. It only has 5 numbers on it. And very short key. This is like from a little teeny tiny, very nice looking safe that has no drill protections, nothing. This lock basically sits right at the door level. So, of course, because we run into this so often, we started thinking of ways to pick these, because of course it's an old, nice, expensive lock, so why the drill if it still works? And actually drilling the lock is not usually easy, especially on a vault door where there's 3 of them. And started looking at these in detail and found that the problems are, where do you tension this lock from? Because everything changes. And with the normal key, once you turn it enough, everything aligns and lock opens. So there's no single place that you can say this is used for tensioning. That little post in the middle of the lock, the round little stem, on some locks it might not be solid, like it might rotate, it's gotten loose or something. And we actually tried making a tensioner that grabs that little post, but it's impossible to rotate it from that post enough to get any feedback from the lock. The picking tip, it's problematic also. Then the lock's tolerances being quite tight makes problems in terms of you have to be exact with your picking. And then we got a very wild idea that I will discuss in a bit. But we thought that the best candidate for the actual tensioning, which is the usual problem in lockpicking, was to find one place that doesn't change that much. And that's the number one wafer in the deepest part of the lock, because the key is always the same on one side. So we went through all our keys and looked at the other side of the key. So how many tensioners would we need? We found at least 7 or 8 different depths, plus that one key with an angled cut. So that got me thinking there might be even more. than just those 8. And the lock, of course, you can test the tensioner in a lock to see if it turns the 45 degrees or not. If it turns more or way less, you know it's the wrong one. But the problem is, like in the previous slides I showed the radiuses, because the key can touch the wafer from the side of the blank, from the edge of the blank, or from the top of the blank. So if you change that radius, also the contact point changes, and you might actually be off with your tensioner without even knowing about it, because you get no solid confirmation regarding is it the right size or not. So we tried this in basically a vise. Just put the lock there and tension from the back, from the little prongs that usually operate the safe mechanism, and discovered that you actually have to tension it quite much with even a large screwdriver to get any feedback from the actual wafers. Like the tension seems that it doesn't click like with a pin tumbler lock. When you're picking, you feel the tensor click a little. With this, nothing. It's just completely dead. And the actual picking tip, because the key is asymmetrical, we got to thinking, well, does the picking tip can it be the shorter one? Is that enough? Do we have to go to the other side of the lock to pick something because there's those split wafers? Is the short one long enough for the long side? Or can we just use one or the other? And we did a little test piece with the picking tool. Can have a quick look. There's nothing special to it. It's a 2-in-1 pick, and the tensor fits a lock. It doesn't fit any other lock. It's just one lock that it actually fits to and works with. So that has the picking tip that is the shorter side of the key, and we discovered that yes, you can pick it just from that one side. You can exploit the fact with the split wafers that one wafer pushes the other wafer, so you can actually use that to get it picked, but it's not easy. Of course, well, Huxley knows this. Regarding tool dimensions, it's always nice to find different ways, but we found that you can actually get away, because there's no spacers to turn the tool within the lock. You sometimes, if you want to get to the other side, it has to be that long pick to be able to pull the picking tip out, turn it around, and push it back in. So consider that there would be this thick door. You would have to get all the tool out and put it back in without losing tension. And that's the reason why on that tool the tension tip is so long. And that's just one length. Maximum 7mm diameter for the whole tool, because that's the largest that will fit in. And all those wafers really, really are precise. That little one example going around here, like I said, has been modified a little with a file to work with a not so correct key. I heard that. But if you find a key, core, and body that has all the same numbers stamped on them, and you turn it to unlock, you realize that the wafers align just perfectly with the core of the lock for it to open. Like everything is the same. And I pretty much think that they actually make the lock so that the wafers are too long originally. They assemble the lock, put the key in, and turn to align the wafers correctly with the key, and then just cut off all the extra from the outside. Because that's basically the only way to get that sort of precision. And that also, I think from the price of the lock, it tells you a lot about the manufacturing process. Like, why would a lock cost €5,000 otherwise? Because any other lock you buy, it's tens or maybe €100. But it's also very, very precise other ways. The wafers that sit in the grooves of the core There's not much slop in them. They're always almost the same. And they're brass, spring-loaded. And everything's basically sitting at the same line. So when you tension, everything kind of binds or not binds. It's hard to actually say. We can actually test this later on a lock in a vise. You can tension it, and from the sides of the lock, if you test with a screwdriver, just pushing the individual wafers, you basically don't find any binding wafer. There's one that kind of felt like it nudged a little, but seems like it didn't move. It doesn't especially set at the shear line. It just moves tiny little amount. We tested this once and we counted over 200 tries with a screwdriver pushing each lever once in a while, the other one holding the torque to get it to open, and took half an hour. I don't even want to know how long does it actually take with the pick that is going here. But I'm guessing at least half an hour. So the wild idea was because the wafers do have some similarities in the keys, or actually keys are always the same in some way. The cuts are known. I've heard from other sources that you can actually send a key to the factory or just some dimensions of it, and they can actually make new keys or a copy of the key. So I think the actual cuts in a key have been standardized. So the depths are known, the angles are known, the positions are known. It's just the wafer actually that change. So you could maybe do a makeup key that you can just put one piece in and test if the key turns enough. Then try another one and so on. But the problem is when we started, after this idea, we started measuring those key turning angles and found, well, it's 42 to 50 degrees, and that is just from 30 locks. Well, what is the correct thing? If you make a makeup key and it turns 46 degrees, is it correct or not? Maybe it turns 43 degrees, is it correct or not? You have no way to confirm that thing. And inside the lock, there basically is no space to put some shim between the wafers to find where the edge actually is inside the lock. So technically it could be done, not so well. I don't think it's worth it. These are basically, well, the only resources I know in terms of this lock currently. There may be more. This is something that you just get a picture here and picture there. The Coxa website actually has pages and pages of stuff regarding the old patents and what changed, what year was things happening, and some little photos of the different models. And Leptig is now the one who actually sells the lock and or manufactures or manufactured. I'm not sure. There's a lot of rumors going on, and it seems that nobody is ever sure of anything. Formerly it was Kromer. Of course, it's a Kromer protector lock, but now it's Leptig who apparently is the one responsible for the keys and all. Their website is basically non-existent in terms of there's a page that says, well, welcome, we sell locks. I'm like, okay, well, what do you sell? There's nothing in there. But thank you. I think my time is almost up. So if there's any questions, stupid ones, not so stupid ones, happy to answer. Huxley?
What about impressioning or self-impressioning?
So Huxley is asking, what about self-impressioning or just impressioning the lock? Would have to actually test it, but I think not in terms of you can tension the lock. So self-impressioning tool would be hard to make. And impressioning, well, I don't know, because the lock just is so dead, even for picking attempts. I don't know how well would it actually mark a key, and especially because you don't know if the key cut is angled or not, or what portion of the key actually touches the wafer, so it might be difficult to make the cuts. Some cut may actually jam in the lock in terms of it might bite into the wafer if it's not correctly rounded. So plausible, can't confirm nor deny. Anything else? Good information that I don't know. And that's it. Thank you.
Thanks, Jaakko. I hope everyone gives the lock a try.